Hi everybody, and welcome to my second Hardware Tales video. A few months ago I bought a Atari 1040STf and I spent some time restoring it and doing some hardware upgrades. And I want to show that to you now, and I hope you enjoy it. So without further ado, let's start. So this is the machine I got. It does not look too shabby, I think. It's slightly yellowed, pretty dirty, and there are even some insect cocoons all around the thing. Before I boot the computer for the first time, I usually check if there is something wrong with the mainboard, like some leaked capacitors or anything that could create a short circuit. So I'm opening it up and taking a look. During disassembling, I found quite a lot more dirt, including some mildly disgusting curly hair. There were also some stains from some liquid that I could not identify, and of course more dust. Then I removed the keyboard and I found some corrosion on the RF shielding of both the computer and the power supply. Here's the inside of the power supply, and it looks good as far as I can tell. The capacitors don't leak and the fuse looks good too. On to the next layer. I removed the mainboard's RF shielding and took a look at an Atari ST mainboard for the very first time in my life. This is the famous Motorola 68000 CPU. It's an interesting design. It works like a 32-bit machine, but only uses an external data bus of 16 bits. Here's the RAM, 1 MB dynamic RAM in 2 banks of 16 chips. Each RAM chip attaches to a single data line of the data bus, so they must always come in groups of 16 to feed the 16-bit external bus of the 68000. These are the ROM chips, which contain the BIOS and operating system of the Atari. I had never seen a design with 6 ROM chips before, so I had to do some research. Each of these chips has a size of 32 kilobytes and a data bus width of 8 bits. That's the reason why always 2 of those chips are combined into one set that makes the complete 16-bit data bus of the Atari ST. And that's also the reason why half of them is labeled as high, while the other half is labeled as low. Okay, continuing to check the capacitors, but it turns out they all look good and there were no metal bits or other things causing any short circuits. Actually, I forgot to check inside the shielding of the shifter, which is the video chip, but as you will see shortly, nothing bad happened because of that. Something I did notice though was that whoever worked on this machine before bent some parts of the mainboard shielding, so I fixed that real quick. Now with all the preliminary checks out of the way, I was ready to turn on the machine for the first time, and guess what? It works! A quick check shows that this is version 1.00 of TOS. The version is not shown anywhere, but the copyright line only contains the year 1985. That's the same year I was born in, by the way. A very good year, that 1985. Anyway, the only version with that copyright line is 1.00. I read that it has a few bugs and is slower than the new versions, so at this point I decided to find out how to upgrade the ROM in this machine. But first things first, the machine was so dirty that I didn't feel comfortable even touching it, so I decided to clean it first. A very good method to clean old computer parts is to just take them apart and put all the plastic stuff into warm soap water and leave it there for an hour, and then just brush it with a toothbrush and let it dry for a day. That usually gets rid of all the real nasty stuff on the case. I didn't want to take the whole keyboard apart, so I just decided to clean it with some alcohol, cotton pads, Q-tips, and this is the result. Now came the fun part. Call me awkward if you want, but I actually, honestly like putting a keyboard back together. It's like a weird puzzle where you know exactly which piece goes where. That's not entirely true though, because I'm not familiar with the ST's keyboard. I usually start with the easily recognizable keys, like the function keys, Control, Alt and so on, and then work my way through the letters. The only thing left to do before I could finally start using and exploring the computer was to reassemble it. The first time it was a bit difficult to not forget any small screw and to put everything exactly where it belonged. I've done it about 20 times after this first try, and I think I can do it blindfolded now. The first thing I wanted to do was to try an old German shareware game called Ballerburg, which only needs a monochrome monitor. So I used another part of high tech to download the game and copy it onto a floppy, and try to start it on the Atari. But then this happened. TOS error number 35. I thought maybe the disk was bad, so I tried a different one, but that didn't solve the problem either. So I opened the floppy drive to check if it seemed to work normally, but I don't have much knowledge about floppy drives, so all I was able to do was clean the read heads, and that didn't change anything. So because I have so little knowledge about the electronics of a floppy drive, I decided to use a PC floppy drive instead, which are basically the same and they are interchangeable and you can use either drive on either machine. But the downside or the problem is that those floppy drives can be configured to different drive units. So you can assign drive unit 0 or 1 to a floppy drive, and that will decide if it is a drive A or drive B. And the thing is, when IBM designed the IBM PC, they decided they didn't want the user to have to configure the drive, and instead they used the cable to select between different IDs. That's the reason why on a PC floppy cable you have this weird twist that basically just swaps a few cable pairs that make sure that the floppy drive on the far end of this twist will be recognized or will have the other ID than is configured on the drive. And for some reason, they decided to configure all PC floppy drives as ID 1 instead of ID 0, which would on the ST be drive A. So I want my drive to be configured as ID 0 to be detected as drive A on the Atari, but all PC floppy drives are actually configured as ID 1. Luckily, I found one drive that allows configuring between drive ID 0 or 1 by setting the jumper on the back. After doing so, I was able to connect the drive to the ST in a weird position. That was needed because my drive's connectors rotated 180 degrees compared to the old drive. I didn't want to stress the connector cable by twisting it to make it fit, so this had to do for now. Next try with the game and bingo! It loads fine. So the floppy controller is good, the drive is bad. At least I have a replacement drive, right? Wrong. The Atari has a very old drive that is actually higher than newer drives, and it has a radically different front panel. I really hate it when people alter the visual appearance of their vintage computers irreversibly. So it was out of the question to just cut out a new opening for the drive. I had to tinker a bit with the old drive's front panel and the new drive to make everything fit together. First, I had to figure out how to line the front panel. That was more difficult than expected because the new drive's eject button mechanism was in the way. So I decided to take a radical approach and just cut that little protrusion off. It really wasn't easy, but in the end I won. But was it enough? Nope! There were more metal bits in the way, so they had to go too, which they did. Another fit check, and it seemed to work. The front panel fits onto the drive like a glove. So, I was done with the floppy drive replacement, right? Wrong again. The eject button needs to be quite a bit lower on the front panel than it is on the new drive. I had to mount it somehow. When you thought this floppy replacement action was pretty hacky so far and you're already biting your nails in horror, then please skip the next part because it's going to become even less professional. And here it is, my magnus opus of metalworks. I cut it from some spare metal parts, I don't even remember exactly what it was. But it fits perfectly and is now held in place by some glue and tape. So I glued the front panel onto the drive and was finally able to tackle the last real difficulty. The drive has to be mounted a bit higher than the old one so that it fits into the opening in the case. That was a slightly annoying task because I wasn't really able to measure exactly how much spacing I needed, so I tried different spacers. In the end, I settled for some HID mounting brackets from one of my PC cases. They happened to have the perfect height for the task. Sadly, the added height moved the threading for the screws too far away, so I first had to buy some screws in the right length. Oh, and I had to rip 2 of the wires on the ribbon cable apart so that I could twist it and plug it into the newly mounted drive. So, in case you're wondering if this replacement is perfect, no, it's not. For one, the mounting does not seem to be quite right because sometimes the floppy gets stuck inside the case. Another problem with this approach of repairing or replacing is that the new drive does not send any disk change signals to the operating system. So whenever I replace the disk inside the drive, the operating system will not notice, and the file explorer or file browser of the TOS will show the old files and create all kinds of havoc. But I honestly think it's good enough for now, because from the outside it looks like nothing ever happened, and it's working good enough for me, really, for now. But if any of you have an idea where to get a replacement Xenon FB354 drive for my ST, or how to repair or what to try with the old drive, then please let me know in the comments. Another thing I wanted to do was to make a VGA cable for the machine. I only got a monochrome monitor with it, but it actually generates VGA compatible signals. Most new monitors complain about the signal though, because it has lower horizontal refresh rate than modern displays expect. Luckily, I own several older screens that support that refresh rate. Finding the appropriate plug was not easy though. It is a 13-pin DIN plug that is barely sold anywhere. I found one though and ordered it. It turned out though that finding it was easy compared to actually soldering wires onto it, especially with my mediocre soldering skills and ancient soldering station with way too big a tip. I used an old VGA splitter cable that I don't use because it darkens the image quite a lot. I cut one end off and used that as a new VGA connector that I can plug any VGA cable into. The same port is also used to output a mono audio signal, so I added an audio jack. Here's the final product. It works perfectly fine, and I actually found out that my normal, everyday work 24-inch flat screen accepts the Atari's VGA signal. And that's pretty cool, because it means I don't have to stare at a CRT for extended periods of time. And this is actually giving me headaches lately. I guess we are not used to flickering screens anymore with our modern LCD and TFT and whatnot. So whenever I have to look at a CRT nowadays, it gives me headaches. So, with all the more or less easy parts done, I only had 2 things left to do, and one of them was to actually finally upgrade the operating system ROMs. To do that, I thought it would take me maybe a week or 2, but it actually took me more than 2 months to complete this project, because I first had to learn how to etch PCBs, I had to learn how to program ROMs, and actually I built a ROM programmer just for that purpose, which is open source now. You can download it and build your own hardware using the schematics that I made and using the software that I made for it. I had to order parts from different places for this. It was a lot of waiting and some nail biting in the process, but if I managed, find out. So I searched the internet for the schematics of the ST mainboard, and I found this. And though this is the page that describes the ROM chips on the ST mainboard, and as you can see, there are 6 of them, and 2 of them always combine into one data word of 16 bits. Because, as I said before, each of these chips is providing 8 data bits of data, and those combine into 16 bits each. So same goes for them. They go together and form a part. And depending on what address on the ROM is requested by the CPU, there will be a different set of these active. Either these 2 are active, or these 2 are active, or these 2 are active. And that's all depending on these lines, which are chip select lines. So as you can see, those go here and here. This line is going into this chip, and the same. This one is a bit special, but in the end you can see it's routed through here and through here. Right, so this is how the 265 kilobit version is working. So each of these chips has 265 kilobits. But the old ST mainboards also support 1 megabit ROM chips. So each of these can either be 265 kbit or 1 megabit. And to select between those modes, you have to choose or set the values on these jumpers. Depending on how those are set, these are hardwired to either ground or 265, yeah, sure, or 5 volts. And depending on that, different things happen with these chips. Or in the special case of this one, it can be selected to do some combination of the lines, which I will explain in a short while, or circumvent or bypass this component and go directly from the ROM select 2 line right into both chips. Excuse my horrible drawing. What does this component do? It's a 74LS11, which is a AND gate with 3 inputs. So what happens is when either of these 3 inputs goes to 0 or 0 volts, the output will also be 0. And if all 3 are on at 5 volts, it will output 5 volts. So that's a typical AND gate behavior that produces the logical function AND. Interestingly, this symbol should be an AND if I know my American logic symbols, but the name here actually says it's an AND gate and not an AND gate. The ST mainboard can either use 6 ROM chips using those ROM select lines, as I explained, or it can be configured to use 2 bigger ROM chips that are then only these 2. That works because these ROM chips are exactly 4 times as big as each of the others would have been. So this one is 1 megabit and this one is also 1 megabit, while each of these would have been 265 kilobits. So they are 4 times as big as the other ones. That means it needs 2 address lines more. So the original ROM chips were using 15 address lines and the new ones are using 17. That means those have 2 to the 15th. That's like 32,768. Is that how you speak? Yes. Bytes, because each address addresses 1 byte. And the newer ones, they can address 2 to the 17th, and that's like 131,072 bytes. So 4 times as big. How does that work? The small chips, they are actually not using 1 chip, which is one pin, which is this one. It doesn't have any function on the small chips. That's why it's always wired to a fixed value. But on the bigger chips, this is actually address line 15. So this thing is address line 15 on these chips if those are 1 megabit chips. And the 16th address line, which is here named 17 for some reason, I will explain to you in a second, those are going to pin 22, which is the output enable on the smaller chips. But the bigger chips don't use pin 22 as an output enable. They actually use them as address line number 16, and they don't have a dedicated output enable line. They are always using the chip enable to work as the output enable at the same time, which really on a mask ROM, which you cannot program after they are manufactured, there's really no good reason to have both of them. At least I'm not aware of any good reason to have both of them. Okay, so address line 17 goes then in the new chips there. This is address line 17 of the Atari, and this is address line 16 of the Atari. And those are actually one number one number higher than on the ROM chips, which you will probably understand when you consider that each one of those is only providing those 8 data bits I was talking about. But the address bus is actually 16 bits wide. So here's the data bus that is going to the CPU, and it is 16-bit wide, as is normal for the ST, or the whole data bus is 16-bit wide. And the upper 8 bits of that go to the high ROM part, and the lower 8 bits always go to the low ROM part. And when we take a look at the memory layout, then let's say we have the low address here and the highest address here. We have some stuff here, and the ROM somewhere in the middle. And if we now take a look at this little slice, and let's say it starts at address 1000 hex, and we zoom in, then we see that the addresses are like these, right? And because the Motorola 68000 is a big endian machine, that means that at the even addresses, we have the high byte always of a 16-bit word, and at the odd addresses, we always have a low byte of each data word. And that continues all the way like this. If we now move this to the side and we take a look at the binary representation of the last 3 bits of each of those addresses, then we can see that the upper 2 and everything above that, of course, too, is the same for each of those words. So for the high and the low byte of each word, the upper address bits are always the same. It's the same with those. And at the same time, all of the high bytes have a lowest address bit of 0, while all the low bytes of the words have a least significant address bit of 1. So, and if we now put the CPU addresses up here and the addresses that are used on the ROM down here, then we see that whenever we request either of those, it just changes the lowest address bit of the CPU. But the CPU will always request both of those in a 16-bit request at once. So all we have to do is just look at those bits instead, because those are the only ones that change between the bytes that we are requesting. And that's exactly the reason why the address bit number 17 of the CPU goes to address bit 16 on the ROM chip, and address bit 16 of the CPU goes to ROM bit 15, and so on. I hope that was clear. If not, please let me know, then I will try to explain it better. And if we were using 6 chips, then we would need all 3 of those chip enable lines, because there's some extra logic outside of this drawing that decides which of these lines is active, and it will always activate one of them, depending on which ROM address is requested, or none. Maybe it will activate none if the current address that the CPU is requesting is not mapped to any of the ROM chips. And in the new the 1 megabit version, this piece of logic will make sure that whenever one of those is set such that one of those chips or 2 of those chips would be selected, that then the 2 remaining chips would be activated. So if by default they are all set to 1, which means don't enable the chip. But if one of them goes to 0, then this line will also go to 0 and enable this chip. And it doesn't matter which of those goes to 0, it will always enable the remaining 2 chips. So far so good, but there's one more difficulty, and that is that the ROM chips are so-called mask ROM chips. That means they are created during manufacturing with one specific content, and it cannot be changed afterwards. It's basically hardwired into the silicon of the chip. And if you want to make a home programmable one, an electronically erasable ROM chip, then you need more pins for that. But as I showed you earlier, all the pins on the 28-pin chip are already used in the 1 megabit version. So the problem is, if you want to use a EEPROM, it has to be a chip with more pins. So while a 1 megabit mask-ROM chip has only 28 pins, a 1 megabit EEPROM chip is actually 32 pins, and that doesn't fit, obviously. So I had to make some kind of prototype board or PCB that would hold my new chip and map the pins accordingly. And then I thought, why should I stop there? Why should I use only a 1 megabit chip if I could just use a 2 megabit chip and put 2 different operating systems in there and select which one of these is booted by just adding some kind of switch. Here's my prototype PCB. This was only the second board I ever etched myself. I don't want to go too much into details about this process, but I might eventually make a dedicated video about that. So, once I had the board, I had to drill holes for the parts. A friend suggested to glue a raster circuit board onto it to get more accurate spacing between the drill holes. I did that, and it worked quite well. One thing I learned though is to always drill from the copper side, otherwise the copper will be pushed upwards and creates a burr where the solder doesn't stick very well. I just inserted the IC adapter and ROM socket for a moment to see if I had gotten the spacing right, which I did. Soldering the IC adapter from the wrong side was painful, really painful. As I mentioned before, my soldering skills are not exactly stellar, neither is my equipment. So the board ended up looking horrible, but after checking it and fixing any short circuits I had created, everything seemed to be in order. I needed a way to copy the ROM images I downloaded from the internet onto my flash chips. I didn't want to spend €100 on a commercial EEPROM programmer, so I decided to build my own. I'll make a separate video about that, but for now it's probably enough to tell you that this procedure, including design, etching, soldering and programming, took me about a month. But then I was done and wrote a tiny program to split the ROM images into low and high bytes. I finally wrote them to the flash chips and inserted those into their sockets. My prototype was done. Time to remove the old ROM chips. That's pretty hard to do while holding a camera in a second hand, so please excuse the shaky picture. Before I could actually install my new PCB into my mainboard, I had to change those solder bridges though that I showed you earlier. In fact, I forgot a third one at first and I didn't realize because I was misreading the schematic too and didn't realize there was this third solder bridge, but in the end I realized and changed that. So first I removed the big blob of solder using a desoldering pump and cleaned the pads using solder wick. And in the end, I applied some alcohol to clean the pads and make it easier for soldering later on. And as a last step, of course, I had to add the solder on the new soldering bridge positions. I did that and then installed my prototype board for the first time. Another problem I luckily noticed before trying to boot the thing for the first time was that I actually thought the ROM chips had to be inserted the other way around than they actually are, and I also confused low and high that way, but luckily I noticed before anything bad happened. The first time I booted it though, it didn't work, of course, because I forgot the third solder bridge. So I changed that and retried, and it still didn't work. I was pretty scared at that moment that I might have broken the machine, so I changed the configuration back and installed the old ROMs. Luckily, the machine booted normally. So I spent 2 more weeks hunting down the problem, and in the end it turned out to be 2 separate problems actually. Do you remember that triple AND gate I talked about earlier? Guess what is not installed in my mainboard? So I first had to order those online again and wait a few days before they arrived. In the meantime, I had time to remove the solder in the mainboard before I could then finally install the AND gate into its socket in the mainboard. That also meant I had to remove the bottom part of the shielding for the mainboard, which I had never done before and thought it was hard to get off, but actually it was really easy once I loosened the right clips, or whatever you call them. Getting the solder out of those little drill holes, though, was not as easy as I thought. So I decided to put the mainboard kind of over the edge of the table of my desk and solder from one side and use desoldering pump from the other side to suck off all the excess solder. But then I was done and could finally solder in the new AND gate. After I was done with that, I was sure it would work this time, but it still didn't work. I thought maybe the AND gate didn't actually do what it was supposed to do, so I decided to get out my cheap PC oscilloscope and measure the output compared to at least one of the input bits of the AND gate, but that seemed to look quite as expected, and I was back to page 1. I did not know what was going on. So I spent hours upon hours tracing different things on the mainboard and tried to make sure that all connections were as they were. And I didn't understand what was going on. And finally I realized that the output of the AND gate didn't actually go to any of the two ROM chips that it was designed to go to. I checked a bit more and I finally understood that the schematic was not right. The only schematic I found for the ST mainboard is actually a revision C mainboard schematic. And my mainboard is a slightly older revision B. And you can see those two lines here, those chip select lines that seem to go to high 0 and low 0. On my mainboard, they actually go to high 2 and low 2. Or maybe the labels on my mainboard are just the other way around. Anyway, I just moved my prototype 2 socket positions further and tried again. Do you think it worked this time? It did. Guys, I was so amazed to see this actually work, I couldn't believe it. So I programmed 2 new ROM chips, this time with a TOS 100 in German and a TOS 104 in the UK version, which you can see here. That's also called the Rainbow TOS because of the animated Atari logo in all the colors of the rainbow. And by just removing this jumper, which I would later replace with a switch, of course, I can select the other TOS version. You can already see that this is a German version, and when we check the About dialog now, then you see that this is actually the original 100. So the electronics were finally working and I was really relieved that that actually worked out well in the end. But there was another problem, and that is mechanics. The prototype board just didn't fit into the RF shield of the Atari. That's because the sockets that I put into the board were too high and the whole design was just a bit too much wasting space, and I should have moved the ROM chips over a bit more in the other direction. So I decided to redesign the whole thing and etch a new one and solder a new one and try again. And to be honest, the soldering job I did on my original board was so horrible, I guess that monkey would have done a much better job than me. Here's the new board after I transferred the layout onto the copper. I have to say, I'm getting better at this toner transfer method, but it's still not perfect, and I have to fix up some parts with a marker and other parts with a razor. But after etching, it turned out to be quite okay. This time I actually drilled the holes from the copper side, which made the result a lot better and easier to work with later on. Soldering went a lot better this time, but afterwards I realized if I had just flipped the design and put the IC socket adapter on the back side and the EEPROMs on the front side of the board, then it would have been a million times easier to solder. And all those problems and ugly soldering I got would not have happened. But too late. And it turned out good enough for me. It also turned out to actually fit into the RF shield this time. So, mission accomplished, I'd say. All that was missing now was to find a location for the switch and actually make a cable and put that switch into place. this is where I decided to put the switch, right above the extension port, because there is some free space and it's actually just wide enough to hold a 2-position dip switch. So far, the whole restoration/upgrade project went really well, and I was super happy with the results, and I was confident that this would go on like this forever. But no story is good when it has a happy ending, right? We need bad endings for stories, and as it turns out, this is actually a horror story. If you faint easily, please stop the video now. I'll give you 3 seconds. Here's what happened. I decided that I didn't like the slight yellowing on the Atari's case, and I said I wanted to try Retrobright for the very first time. And that turned out to be a horrible idea. First of all, the result after applying it and putting it into the sun for a few hours turned out to be a cloudy mess. Some parts of the plastic were almost white, while other parts were still a very dark gray, as it was supposed to be. So I thought maybe I hadn't applied the Retrobright evenly enough, so I retried, and that didn't make it much better, and I tried a third time, and that was a really horrible idea. Now, as it turns out, some parts of the case are actually almost white, while the others are still gray. It didn't even out at all, no matter what you did, and apparently what I found out later in the internet was that this is a common problem for the ST and also other Atari computers and very early Apple computers. They don't really like the retrobrighting. Apparently some part of the dye inside the plastic gets dissolved or reacts with something in the retrobright. It's a horrible idea. Don't do it. If you do, don't say I hadn't warned you. Are you ready? Do you want to see the result? So yeah, that's the result. I'm really disappointed, and I was thinking about painting it or trying different things to repair it, but in the end I think I'll just leave it the way it is, and that is for 2 reasons. First of all, because it will serve as a reminder to be very careful with old stuff and not try chemical experiments without knowing what I'm doing, and not without trying them on a spot that's not so clearly visible. Maybe I should have tried a small spot on the inside first, and once that would have worked out, maybe it would have been better, but yeah. And the other reason is that by painting it, I would probably just make it worse, thus applying rule 1. I will probably not do it. So that's what my Atari looks like now, and that's what it will look like in the future. On the other hand, the keyboard does look very good. So at least that worked out quite well for me. But the overall project is quite the failure. So that's the end of this video. I hope you enjoyed it, even though I failed miserably in the end. If you have any ideas how to fix my problem without ruining the case even more, I would be very glad to hear about it. The same goes for the floppy drive problems that I talked about earlier. If you have any idea how to get a better drive or a new drive or repair the old one, please tell me. And there are also some other projects that I have planned for the future. I have several computers that I haven't done anything with yet. I'm going to make some videos about that very soon, and I hope you come back to watch them. So long. Bye.